Probably not. Can you hear me now?
Yeah.
Awesome. Okay. So does anyone have any questions about anything that we talked about so far?
No, I don't think so.
Okay. Well, if that's the case, then I'm just going to carry on with lecture, and we're going to talk about electrons. So we talked about the subatomic particles, the protons and the neutrons, and those are found in the nucleus. So we have, it's kind of like the Earth, and we have protons and neutrons, which are found in the what we call the nucleus, just like the nucleus of a cell. And then spinning on the outside of these things are the electrons, which we have, the symbol for electron is the E with the negative sign because they're negatively charged.
It's not showing your screen.
Oh, thanks for saying that.
No problem.
All right, so zoom, share screen. Can you see it now?
Yeah.
Okay. All right, so what I was drawing over here is that protons and neutrons are in the nucleus, just like the nucleus of an atom. I'm sorry, of a cell. So the nucleus of an atom is just like a cell. You can kind of think of it as like the Earth, and then the electrons are revolving around it, sort of like satellites or the moon, except these things are moving at the speed of light. They're moving at 186,000 miles per second. So it ends up turning into what we call an electron cloud. And there's different shells that these electrons take up. So you can kind of think of it as like a bookshelf. So let's say that you had a bookshelf at home. It's a funky shaped bookshelf. It kind of goes more like this. And so if you had a bookshelf and you had books, there's only so many books that you can fit on a shelf. And when that's full, then you have to go to the next shelf, right? And when that's full, you have to go to the next shelf. And so this is how these orbitals of electrons are. You have the first orbital, and then you have the second. And when that one's full, you have to go further out, and that'll be the third, and so on and so forth. So these orbitals are kind of like bookshelves. Once they're full, you have to go to the next orbital or the next shelf. And these orbitals help determine this electron configuration, which is where these electrons are in the atoms. The thing that's really important here is that if we were to look at the first shell of any particular atom, the distance of that shell would be several miles away if we were gonna, let's say the nucleus was the size of a golf ball. So that means that when two atoms come together, the first things that are ever going to encounter each other are the electrons. Like the nuclei never come close unless they're in a particle accelerator or there's some sort of nuclear decay going on. But any chemical reaction is only going to involve the electrons because they're so far away from, in relative sense, from the nucleus. Does that make sense to everyone?
Yeah. So they have nothing to do with the protons?
Well, they do. So the number of protons equals the number of electrons, right?
Okay.
But because the electrons are so far away, kind of like how the moon is to the Earth, like if the Earth was going to fly off its axis and go into the sun, what would be the first thing to hit it, the Earth or the moon?
The moon?
Yeah. And it's the same thing with atoms. So
Okay.
if you have two atoms coming together like sodium and chlorine, the first thing they're gonna encounter are the electrons. The nucleus would never encounter each other first. Does that make sense? And
Yeah.
so that means that the chemical reactions that happen all the time are due to the electrons, not the nuclei. The nuclei determine the number of electrons, but it's the electron interacting with other electrons that cause chemical reactions.
Okay.
Okay, so this is sort of what you would learn in chemistry. I don't care that you know this. Um, or, orbitals have different shapes, and electrons are weird. They can be matter and energy, and they can change back and forth. In fact, if you walked into a wall for 10 trillion years, eventually all your electrons would be energy, and you'd be able to pass through the wall just by random chance. But that never happens because nobody has that amount of time. And there's something called the uncertainty principle, and it has to do with a thing called Schrodinger's cat. And that has something to do with not being able to predict where electrons are unless you observe them. And once you observe them, then you've changed the way where they are found. I know it's confusing, but in reality, the electrons in your body could disappear and start orbiting around the moon, not all at the same time, but individual ones, and then come back. And so it's called this spooky matter, and it's bizarre, but it's in physics, and you don't really need to know this for this class. What we want to know is what is in the outer shell of the atom. In other words, what's the electron configuration? And this is drawn here. So here's the rules. We have the nucleus that's shown here in gray, right here. And then we have the first shell, right? So every atom in its first shell has two electrons, and they're always paired. They spin in opposite directions, but you don't need to know that. So just like this is drawn, the first shell has two electrons. Then we go to the second shell. So we can come out further, right? Our bookshelf is full. It can only hold two electrons. And then the second shelf can hold eight. And again, they're always paired. It, the actual way that you write these in, and I'll write a third shell here because the third shell also can only hold eight, and so on and so forth. So everything after that is eight. That's not really true. So when you get to chemistry, your chemistry teacher is going to teach you that when you get to level 4 and 5 and so on and so forth, they take on these different p and z orbitals and y orbitals, and you can get more electrons in a shell, but they're on a different plat. I don't want to confuse you. Let's just stick to this thing. It's called the octet rule. And what that means is that besides the first shell, every shell after that holds eight. And the way they fill is they fill unpaired. So if we were going to fill this outer shell, we would start here and we would go clockwise. This drawing is kind of in the way, but I would normally put it over there. And then we would go around. So there would be 4 unpaired, and now they start pairing. So now there's only 3 unpaired. Now there's 2 unpaired, right? Can you guys see that? And then 1 unpaired, and now there's no unpaired. Any questions about that?
No.
Okay. So basically what I've drawn here is the So this atom would have an atomic number of, can you guess? So all we have to do is count the electrons. So we have 2,
Is it 20?
4, 6, 8, 10, 12, 14, 16, 18. So this atom would have an atomic number of 18. Okay. And just to go with the example that's here, so we could erase this outer shell. And what would be the atomic number of this atom that I've drawn up here? This is also called the Lewis structure, or the Lewis dot diagram that just shows the electrons in the outer shell. So what would be the atomic number of this particular atom here?
10.
All we have to do is count out the electrons. So we have 2 in the first shell, 8 in the second. So what does that mean?
10.
Yep. And it turns out that neon has an atomic number of 10 and an atomic mass of 20. So it would have 10 protons, 10 electrons. How many neutrons?
10.
Remember, to figure it out, you take the atomic mass minus the number of protons, and that gives us 10 neutrons. All right, so it has 10 electrons, 10 protons, and 10 neutrons. And that's the kind of stuff that you guys are going to have to figure out from the exam. If I give you the mass and I give you the atomic number, you should be able to tell me how many protons, how many neutrons, and how many electrons, and where those electrons are located. Any questions about that? All right, let's do a practice one. And you guys will have a periodic table, so let me pull one up. Okay, so can you guys see the screen?
Yeah.
All right. So the periodic table here is for sodium. It's not really showing the mass, so this is kind of a cruddy table. Let me see if I can find a better one. It's kind of hard to see. Well, anyway, I can just tell you that sodium, this is small. It's still kind of small. Anyway, you probably can't see this, but the atomic mass of sodium is 22.9, which rounds up to 23. So the atomic number is 11. So if we go back to the PowerPoint here, we can write this out. So sodium is 23 is its atomic mass, and 11 is its atomic number. So now let's break it down into its subatomic parts. So if its mass is 23 and its atomic number is 11, how many protons?
Is it 12? Oh,
So remember the atomic number is the same as the protons. So this would be 11. And then the number of electrons. Remember
they're the same. So it's 11.
Right. Remember the rule is the number of protons always equals the number of electrons, because these are in an electrically neutral atom. So everything we're talking about is neutral. It means it has a 0 charge. So if it has 11 plus charges, it also needs 11 minus charges, and these cancel each other out. And then how many neutrons?
12.
Yep, it's perfect. Okay, now we want to focus on these electrons, because these are going to interact and cause reactions. So I'm going to jump over to this side, and we'll draw out that Lewis dot diagram. So we have our first shell. We're going to ignore the nucleus because we don't really care about it. It's not going to react with anything. So our first shell can hold how many electrons?
2.
2. The first one. So we draw 1, and then we pair it. This is the first shell. And then the second shell can hold how many?
8.
Yep. And remember, we go around it. So we're going to go counterclockwise and not pair them until we come back. So there's 4 sides of this. And so we have 11. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And now that shell is full. So we have to go to another shell. There's no half shell. There's no anything like that. There's no half bookshelf. And so how many electrons would be in this third shell for sodium?
2.
Yep. Just 1. So we have 1, 2, we can double check. 2, 4, 6, 8, 10, 12. Oh, sorry, 11. 2, 4, 6, 8, 10, 11. So this is 11 electrons. So it has 1 electron in its outer shell. And that's really what we want to know. How many electrons are in that outer shell? Because this is the first shell that's going to encounter anything else. So now we can do the same thing for chlorine. So I'm going to erase this. So we're gonna make some salt. Okay, so for chlorine, I'll just go back to the periodic table. So it's probably kind of hard to read here too, but chlorine is weird. It's like 35.5. So it's because it's 0.4, we just round it down. So we're going to call this 17 and 35. All right, so let's go back. So you'll be given its mass is 35. It's really 35.5, but for this exercise, we'll just use 35. And then its atomic number is 17. So how many protons does it have?
17.
Yep. How many electrons?
17.
Perfect. And how many neutrons? So remember, to figure that out, we just take the atomic mass minus the atomic number, and that gives us, right? Okay, so that's great. All we really care about is the electron. So I'm going to erase this, and then I'm just going to show you the electron configuration for chlorine. So just everybody remember, we have 17 electrons for chlorine. Okay, so this is sodium. Dang it. Okay, this is sodium. This is chlorine. I'm gonna have to draw this a little smaller because chlorine's bigger. So first shell, how many electrons?
2.
Good. And then we have to go, that one's full, so we have to go to the next one. This is the second shell. And how many electrons?
8.
Right, so we'd have 17 electrons. So we can draw these out and they only pair when they come back like this. And so that gives us 10, so we're still missing 7. So we have to put another shell out here. And so for chlorine, its third shell has, so we have 10, so we need 7 in this shell, right? Everyone agree with that?
Yeah.
So 1, 2, 3, 4, 5, 6, 7. And so chlorine has one unpaired electron in its outer shell. This we don't really care about for right now. We just want to know what's in the outer shell because this is that shell that's going to run into this shell. So when chlorine and sodium come together, what happens is that these atoms want to have their outer shell filled, right? And so sodium, it needs 7 more electrons to fill it. So it can add 7 electrons, or it can lose 1 electron to have a full shell. Does that make sense?
Yeah.
And this one, it needs to add 1 electron to get a full shell, right? Because it's missing 1, or lose 7. Now, what do you think is easier to do? Gain 7 electrons or lose 1?
Lose 1.
You'd be right. And then for this, what do you think is easier to do? Gain 1 electron or lose 7 electrons?
Gain 1.
Perfect. So chlorine is going to come up to sodium, right? You can just think of them as people. And chlorine's going to go, hey, sodium, you're not happy. You have this extra electron that you need to get rid of, right? And I want that electron, right? So if you give me that electron, we'll both be happy. And sodium goes, okay. I mean, this isn't really real, but they're in the chemical world it is. So sodium gives up its electron, right? So now chlorine has a full outer shell. Do you guys see that?
Yeah.
But remember, its atomic number is 17. So it has 17 protons. And now it has 18 electrons. So what's the charge on protons? You guys remember?
17.
It's plus. So it's 17 positive charges. And then what's the charge on electrons? They're negative. So if we have 17 and we subtract 18, that gives us -1. Does that make sense?
Yeah.
So this now has a -1 charge because it gained that electron, right? It's no longer electrically neutral. And sodium has gotten rid of this electron. So sodium's atomic number is 11. So it has now 10 electrons, right? And they're minus, so that's -10. And then it has 11 protons, which is plus 11. So what's the charge on sodium?
+1.
Yeah. So this charge is +1. And this charge is -1. So what happens when you have a negative magnet and a positive magnet and you put them together?
Are they drawn together?
Yeah, they're stuck. So by sodium giving chlorine its electron, they've automatically become magnets and now they're stuck together. And what do they make?
Salt.
Salt. That's exactly right. So you have this explosive metal and this deadly gas, and they react to form table salt just by the transfer of this electron. So that's why these outer shell electrons are really important. And you guys need to know how to figure out these electron configurations. So it's just going to take some practice. Print out that periodic table that I put a link to in the announcements, and then just start practicing on various elements. And you can double check your work on Google to see if you've done it right. But what you need to be able to do is for any element, you should be able to know the number of protons, neutrons, and electrons in the neutral one. And then you should be able to draw or predict how many electrons in its outermost shell. Does that make sense?
Yeah.
Awesome. Okay. So that's how we predict chemical reactions. And we're going to get more into this as we go along. But what I want to talk about right now is how energy works based on this atomic nucleus. So we have our first electron shell, our second electron shell, our third electron shell. So let's imagine that you were on a rocket ship and you're going to the moon. So here's the moon and here's the Earth. So in order to get to the moon, you need more and more energy. Does that make sense? The further out you go. And so that energy has to come from somewhere. That energy could come from anywhere, right? On a rocket, it would be like liquid. So Elon Musk, his new thing is that he's using liquid methane. They used to use hydrogen and oxygen, but his plan is that Mars has a lot of methane trapped in it. So he's going to make his rockets run on methane because when he gets to Mars, he needs to get a way to get back. So, but it could be oxygen or it could be anything. I mean, it could be sunlight, right? So if sunlight, because sunlight has energy, and we know that because solar panels and plants grow and all that stuff. So if we put energy in, what does it make our rocket do?
Go farther.
Yeah, it's going to go further out. So when we put energy in, it makes these electrons, because the electrons are kind of analogous to the rocket, they're going to go further out, right? And what comes up, right? Let's say you didn't get all the way out of space. This is the space barrier. Let's say there's only enough energy to get up to here. What would happen then? What would happen to your rocket?
Would you get stuck or fall back?
Yeah, it comes back down, right? And when it comes back down, it smashes into a million pieces and explodes, and all that energy is released. So energy, when we absorb energy in an atom, it goes further out like the rocket. And when we lose energy, it comes back in. And that energy gets transferred into something else. The reason I'm telling you this is because this is how photosynthesis works. Light energy comes in, excites these electrons, and causes them to shoot further away from the nucleus. And the further they get, the less pull this positive charge has on it, right? So the further you get away from the Earth, the less gravitational pull you have. So chances are, if you miss the moon, what would happen?
Kind of just float.
Yeah, you just float into outer space. And so if we put enough energy into atoms, their electrons will go away. They will leave the atom. And this is how photosynthesis works. And we're not going to get to this until chapter 10, but I just want you to understand, since we're talking about electrons, how this works. that make sense?
Yeah.
Okay. All right. So this is what you should be able to do with these elements, right? So if I, on the test, I said, here's boron. Its atomic number is 5. How many, I would have to give you the mass to figure out the neutrons, but right now we're just trying to figure out the electrons. So if we're going to draw boron, what would its electrons look like? It would have, if its atomic number is 5, how many electrons does it have?
5.
Yep. So now we just got to draw it out. We know that 2 goes in the first, and then in the second we would have how many?
3.
They wouldn't be paired. We would go 1, 2, 3. So if I'm right, then this should look just like this, and it does. Does that make sense? And if I gave you, oxygen on the test, and oxygen is 8, so how many electrons in oxygen?
8.
And so you should be able to draw the configuration of oxygen. So first shell, 2 electrons. Second shell, how many? 6, right? So 1, 2, 3, 4, 5, 6. And if I'm right, then oxygen should look like this, and it should have 2 unpaired electrons in its outer shell. So let's see if it does. And the answer is yes. 2 unpaired electrons in its outer shell. Does that make sense?
Yes. Yeah.
Okay. So here's a new word, like foreign language. Remember, we're going to talk about this thing called valence. So valence is the number of unpaired electrons in the outer shell. So in this case, what's the valence of lithium? How many unpaired electrons in its outer shell?
1.
Yes. So its valence is 1. And hydrogen, how many unpaired electrons in its outer shell?
1.
1. So its valence is 1. What about helium?
0.
Yes, 0.
No.
So this isn't going to react because it's happy. Its shell is full. What about oxygen? What's its valence?
2. No.
Perfect. And carbon?
4.
Yes.
No.
So this predicts how many bonds everything can make. Hydrogen can only make 1 bond because its valence is 1. Oxygen can only make 2 bonds because its valence is 2. Carbon can make 4 bonds because its valence is 4. Does that make sense to everyone?
Yeah.
And that's how we can predict the structure and the reaction of this. So what's the formula for water?
H2O.
Now, why is it H2O? Why isn't it H4O or H3O or HO?
Because oxygen can hold 2.
Right. Oxygen to be happy has to make 2 bonds. And hydrogen has to make 1, right? So
Yeah.
oxygen needs 2 hydrogens, and hydrogen needs 1 oxygen. So everybody's happy, right? Hydrogen has its 1 bond, oxygen has its 2 bonds, and that's why water is H2O. So we can predict the chemical structure and formulas of not only things like water and sodium chloride, right? Because we know sodium's valence. How many unpaired electrons here? Well,
1.
right. And then chlorine has 7. So its valence is, well, it has 1 unpaired electron in its outer shell, right? So these each need 1. And this one actually gives up the electron to this. All right. So everybody understand valence?
Yeah.
Is there ever a chance where it's just they've joined together, but there's still an extra electron floating around, or no?
No, they would not. They wouldn't be happy that way. So they would be very reactive. They would be wandering the Earth. They would be very sad because they didn't have their outer shell fulfilled. So they would wander the Earth until they found someone to share their life with and to make their electron shell whole. Does that make sense?
Yeah.
Now nitrogen's weird. Because remember we talked about to make your outer shell full, you'd have to gain for nitrogen. How many would it need to gain?
3.
3, right? Or how many could it lose to get rid of all those to make the first shell full?
3.
Well, how many's in the outer shell?
5.
5. So it could gain 3 or lose 5. Because it's right in the middle there, sometimes it will do this. Most of the time it does this. So its valence is 3, but sometimes it can form 5 bonds. You really don't need to know that because we're going to kind of stick to this. But I just want you to be aware that this one is one of those exception molecules. All right. So we talked about the octet rule. Everybody understand that that's every shell above 1 holds 8 electrons, and the first shell is 2.
Yeah.
Okay. No?
Yeah, I got it.
Oh, okay. Somebody else. All right. So, all right. So we talked about transferring electrons when we talked about sodium chloride, right? They transfer the electrons. Sodium gives up an electron to chlorine, and then this one becomes positive, this one becomes negative, and then they're stuck together. And they're stuck together unless something interferes with it, and water can do that. So if we add water in, these things can separate because water also has a charge, and we'll talk about that in chapter 3. And that's how water can dissolve salt. So we'll talk about that, but it's always the valence electrons, right? Okay, so this is a new term, valence electrons. And I just want to clarify this. I'm going to go back. So there's a difference between valence and valence electrons. So let's look at oxygen. So oxygen's valence is 2 because it has 2 unpaired electrons. But its valence electrons are actually how many electrons in the outer shell, which is
6.
Yeah, so oxygen hang on. So this is kind of an important and confusing concept in chemistry. So oxygen, which is O, its valence is 2. Its valence electrons is 6. This is the number of electrons in the outer shell. This is the number of unpaired electrons in the outer shell. And there's 2 different terms. All right. So we either share or transfer electrons, and that produces chemical bonds. So this particular kind of chemical bond where the electron's transferred is called an ionic bond. But sometimes they have to share, and if they share, they're called covalent bonds. So transferring is ionic, sharing is covalent. And we have to make a distinction between those two because one bond is stronger than the other and it has different properties. Some are reversible and some aren't. So I'll give you an example. what happens if you breathe in carbon monoxide?
Her mom and dad. That
You
her
die.
mom and dad.
And what happens if you take cyanide?
You die.
All right. So carbon there. So we're going to learn this in chapter 9. But there's a thing called an electron transport chain, and you can think of it as a vacuum cleaner cord, right? So what happens if you cut the vacuum cleaner cord? Does your vacuum work?
Can
No.
I hear again?
This is really important to make energy. So if we cut this, we can't make energy, and you guys can't live very long without energy. Just hold your breath and you'll stop making energy. How long can you make it? Not very long. So carbon monoxide poisoning binds to this in the same place as cyanide. The difference is this is a weaker bond because it's ionic, and this is a stronger bond because it's covalent. So if someone came into the emergency room and said, I accidentally took cyanide, you could tell them, well, basically, there's nothing I can do for you because this bond is so strong, it's not reversible. And so, you know, if you took too much, you're going to die. Now, if you came into the emergency room with carbon monoxide poisoning, this is a weak bond and it is reversible. So you could tell that patient, well, I'm going to put you on oxygen. And after a while, this will go away because it's a weak bond and you will be fine, right? You will make energy and this is reversible. So there are two different chemical compounds that act at the exact same place in living systems, but because of the way their bonds are, one can be undone, the other one can't. And this happens a lot in drugs. Like, let's say that you invented a drug that killed pain, right? But that bound covalently, what would happen?
Would it just stay in your system?
Right, and you would never feel pain again. So you would put your hand on the stove. If you broke your leg, you wouldn't know it, right? Whereas most drugs they have to be ionic in nature because you need to be able to undo what you've done, right? There are some drugs that you can take that are covalent, but because your cells are replaced, like Nexium and Prilosec are an example. Those bind covalently to your stomach to inhibit a thing called a proton pump, which makes pH, and we'll talk about that in chapter 3. But the reason that chemical manufacturers can make that, so let's say it's a covalent bond, right? And it blocks your ability to make stomach acid. So if you took Nexium and Prilosec, what would happen?
You wouldn't make stomach acid?
Right. And what do you need stomach acid for?
Digestion.
So you would never be able to digest your food. It'd be like the greatest weight loss drug ever. And it can't work that way because you would die eventually. Right? Because you can't get rid of it.
Yeah.
But you can, and the reason is because the cells that line your digestive system are constantly being replaced. So those cells die off, and then you get new ones that don't have the drug bound to it. So you can continuously make stomach acid. It just reduces it temporarily in the cells. Does that make sense? But you wouldn't want to give that, like, let's say if you had tachycardia and your heart was racing, you wouldn't want to give a drug that slows your heart rate down that's covalently bonding to those cells, because you would never be able to reverse that because your muscle cells are never replaced. And so in the end, that would cause, if you designed that drug, you would cause people to die when you gave it to them because it binds to the heart muscle, the muscles of the heart. Does that make sense?
Yes.
So that whole story is meant to remind you that covalent bonds are strong and irreversible. Ionic bonds are weak and reversible in living systems. All right. So we talked about ionic bonds. Let's talk about covalent bonds. So covalent bonds are caused by sharing of valence electrons by two atoms. I forgot to record this. All right, so anyway, every atom has a strength, right? We call it the electronegativity. This is its ability to keep its electrons. So the higher the electronegativity, the better it's able to keep its electrons. So if two hydrogens encounter each other, the atomic number of hydrogen is 1. So how many electrons does it have?
1.
Yeah. So how many electrons does it want to have?
2.
Right. So it's missing 1. And then this other hydrogen has 1. So it's also missing 1, right? And this is different than sodium and chlorine because these are the same, right? They're like two equally strong people. So if they had a tug of war, no one would ever win. So hydrogen's like, give me your electron. And this hydrogen's like, no, give me your electron. And they go back and forth and back and forth. They know that they're never going to be happy, but they kind of compromise. And so what they can do is share. So this hydrogen gets this electron sometimes, and this hydrogen gets this electron sometimes. Now, I know it sounds weird, but because these things are spinning at the speed of light, they never notice that they don't have 4 electrons total. So this electron is going whizzing around back and forth like this so fast that this hydrogen thinks that that's its electron, and this one thinks it's its electron, and then the other one is doing the same thing. So they both feel like they have 2 electrons in the outer shell and they're happy, and because they're sharing electrons like that, it forms a chemical bond. And this is a covalent bond. Remember, covalent bonds are made by sharing electrons. Does that make sense?
Yeah.
Okay. Same thing with oxygen, right? But oxygen, so remember, oxygen's atomic number is 8. So we can write its electron configuration. We have 2 in the first shell, and then we would have 6 in the second. 1, 2, 3, 4, 5, 6. So oxygen has 2 unpaired electrons. Same thing here. It would have 2 unpaired electrons. So it can share these 2 electrons too. These 2 electrons just spin around, both of them, like so, in a cloud. And so oxygen doesn't know that it doesn't have 8 electrons in its outer shell. But because it's sharing 2 pairs of electrons, then it makes 2 bonds. We call this a double bond. And we'll talk about why that's unique. But these things share because they have equal electronegativity. All right. So we talked about valence. You guys understand that hydrogen's valence is 1 and why. oxygen is 2, nitrogen is 3, carbon is 4. And those are the ones that we talked about the most. Why are these 4 so important?
Because they're in everything.
Right. These, well, in living things, right? These are the 4
Yeah.
big elements, and you'll get that right on the test when I ask you, right? Okay. So electronegativity really determines what's going on here. The rule is that if the difference in electronegativity is less than or equal to then they share equally, right? So we can look at carbon and hydrogen. So if carbon, and we know carbon has a valence of what? Do you remember? It's 4, and hydrogen has a valence of 1. So this will help you out if you guys know these basic valences. That means that carbon has to make 4 bonds and hydrogen makes 1. So this is the simplest carbon hydrogen makeup that we can have. What we want to know is, are they sharing these electrons equally, or are they sharing them at all? And so to find out, we have to know the electronegativities. And I will give you these on the test. And if I don't give you those, they're on that periodic table that I linked in the announcements, and it's on there. So make sure that if you guys go rogue and you print out another periodic table that I didn't recommend, that it has electronegativities on it. So carbon's is 2.5 and hydrogen's is 2.1. So what's the difference between those?
0.4.
So is that less than or equal to 0.5?
Yes.
Then those share their electrons equally. Does that make sense? Now, if the electronegativity difference is greater than 0.5, but less than, greater than 0.5, less than, the cutoff is kind of ambiguous, but we'll call it 2.5, then they share unequally. Okay, so let's talk about something like oxygen and hydrogen. So oxygen, its electronegativity is what? And you guys will be able to look this up on the table. And hydrogen's electronegativity is 2.1. Again, you can look it up on a table, or I'll give it to you. And so the difference between this is
1.4.
perfect. So the 1.4 value here, is that greater than 0.5 but less than 2.5?
Yeah.
So these share unequally. It's kind of like I a few years ago I bought a boat with a friend, and that friend lives in essentially Surprise, right? And so, and they keep the boat at their house because they don't have an association like I do. And so, because they're super close to Lake Pleasant, and I live in Chandler, who do you think uses that boat more?
Your friend.
Yeah. So we share the boat, but we don't share it equally. He uses it more than I do. So that's kind of what's going on here, is that you can share, but not share equally. Whereas carbon and hydrogen, they share equally. Does that make sense?
Yeah.
All right. And to figure out if they share equally or unequally, you have to plug in the numbers. So you can do some practice on this if you want. And if we go back to a periodic table with electronegativities, this is the one that I linked to you guys to. So you can see the electronegativities here. So let's look at chlorine. Its electronegativity is 3. And sodium, its electronegativity is 0.9. So this one's kind of a vague one, but if we got to three minus 0.9 is 2.1. That's really close to this 2.5. And so remember I told you this isn't a hard cutoff. So here, this is so great, the difference between the two, that they don't share at all. Essentially, chlorine goes up to sodium and says, give me your electron. And sodium says, okay. So that's how we can predict the different kinds of chemical bonds.
Is that 2.5 supposed to be less than or greater than?
So if it's less than 2.5, but greater than 0.5. So
the arrow should be pointing the other way. Sorry, I'm just double checking.
no, that's cool. So if X is less than 0.5 or X is greater than 2.5, then they share unequally. But this is arbitrary, so it could be somewhere between 2 and 2.5. All right. So we can do some example calculations here. So oxygen's electronegativity, we can look it up. It's 3.5. And you can see it right here on the table, it's 3.5. So we go back to the PowerPoint. And so we have one oxygen that's 3.5 and it's encountering another oxygen that's 3.5. So what's its electronegativity difference?
Zero.
So do you think they share equally or unequally? Remember the rule is that it has to be less than 0.5. They share equally. Less than or equal to 0.5. If it's greater than 0.5 and if X is less than 2.0 to 2.5, then they share unequally, right? So we would say oxygen shares equally or unequally.
Equally.
Awesome. And what about methane? This is what this is. You'll learn this in chapter 4. So carbon and hydrogen, do they share equally or unequally? So I'll just tell you, carbon's 2.5 and hydrogen is 2.1.
They share equally?
Yes. So if you share equally, right, this is totally equal. This is in that range that it's 0.5 or smaller, then we call that non-polar, right? So when you think of a pole, what do you think of? In magnetism, like the South Pole, North Pole. Well, I normally think of a compass, right? And a compass points to magnetic north. So in order to be a magnet, you have to have a charge. So the term pole essentially means that you have a charge. Now, if the electrons are going around here and they're all shared equally, what's the charge on an electron?
Negative.
-1, right? So since the electron is all being spread out all over this molecule, the ones that they're sharing, then it doesn't have a charge because they're shared equally. Same thing here. There's no charge. So that means that it's non-polar. And because they're sharing, what kind of a bond do we call it? Covalent or ionic?
Covalent.
So new word, if you haven't heard it before, non-polar covalent bonds mean essentially that they are sharing electrons equally. It's just a fancy term for that. You guys have any questions about that?
No.
Okay. This is going to take some practice to get used to this. Okay. Now, oxygen is 3.5 and hydrogen is 2.1. So electronegativity here, difference is 1.4. So do they share equally or unequally? Remember, to share equally, it has to be 0.5 or less. So is that bigger or smaller?
Unequal.
So then they share unequally, which means that in water, here's the example for water. So we drew H2O. This line, this bond represents a shared pair of electrons. And then remember, oxygen has its other ones that are already paired before it met hydrogen. So one of these electrons is being shared from hydrogen and one is being shared from oxygen. So remember, the electrons are spinning. They're spinning like this around each of these atoms so that they're happy, right? But remember, the term electronegativity means atom's ability to keep and hold its electrons. So where do you think the electron spends the most time when it's spinning around water?
Oxygen.
Oxygen or hydrogen?
Oxygen.
Yeah. In fact, might take 3 or 4 trips around oxygen before it takes one around hydrogen. And that means that they're not sharing these equally because hydrogen doesn't have as strong of a grip on the electrons as oxygen. And because of that, it gets what we call a partial or sigma charge on it. Because you would need to take the whole electron to get a full negative charge. Does that make sense? Like in salt. So oxygen has a partial negative charge and hydrogen has a partial positive charge because of this unequal sharing of electrons. And because oxygen is slightly negative and hydrogen slightly positive, then it has a charge. And remember, polar means it has a magnetic charge. So these are called polar, and they're sharing electrons, so they're covalent. So water is polar covalent. Does that make sense?
Yeah.
All right. So this is kind of interesting because if you put salt in water, you guys know what happens. It dissolves. What happens is that the water molecule actually, and we'll talk about this in chapter 3 in detail, but the negative oxygen surrounds the positive sodium. It's kind of like that David Copperfield trick. I don't know if you guys saw this like years ago, but he made the Statue of Liberty disappear. And so when water surrounds this, it's like throwing a curtain over the magician assistant, right? You can't see it anymore. And the same thing happens here, but hydrogen, the positive charge surrounds the negative chlorine. And so we call this a water shield. And these two molecules separate from one another, caused by water. And that's why water is a good solvent. It can dissolve anything that has a charge, which is most molecules. And it has this property of being cohesive, which means that water, if we look at if we looked at water molecules, if you could shrink yourself down and look at water molecules inside a glass. So there's a glass of water. If we could shrink down, we would see that there's a lot of these things floating around in there. There's lots of water molecules in a glass of water, like so. And so these things, because hydrogen has a partial plus charge and oxygen has a partial minus charge, what do you think happens between these two water molecules here? Between the plus and the minus?
Do they connect?
What happens if you put a plus magnet and a minus magnet together? Yeah, they connect. Yeah. So this connection is called a hydrogen bond because it's usually caused by hydrogen sharing with another element, but since hydrogen is really weak. So it's not, this is a very weak bond because it's only caused by those partial charges, not a full charge. Does that make sense?
Yeah.
So cohesion, this is the word of the day. This means water is attracted to itself. And again, we'll talk about this in chapter 3. But just so you understand why, it's these little partial charges, and it's because of the electron, the way that it spins around that compound. Okay. Ionic bonds, we covered this. I think you guys get this. So sodium and chlorine come up to each other. Chlorine wants a full outer shell. It's missing one electron. Sodium wants a full outer shell and it's got an extra electron. So sodium donates or transfers. So chlorine's taking the whole electron. And because of that, it gets a full negative charge. And sodium gets a full positive charge. So if they transfer electrons, this will be on the test. What kind of bond do we call that? That's right.
Yeah.
Ionic, right? If they share electrons, what do we call that?
Covalent.
Cohesive.
Covalent. Yep. Now, they could share equally or unequally. So we have to distinguish between the different kinds of covalent. So if it's unequal,
Polar.
and if it's equal,
Non-polar.
And then what do we call the bond that is caused by that partial charge on hydrogen?
Cohesive.
Well, that's water's attracted to itself, but it could be attracted to other things. Like, have you guys ever filled a glass of water and you could fill it all the way above the top and it makes that sort of bubble?
Yes.
The reason it does that is because water is not only attracted to itself, it's attracted to glass, it's attracted to plastic. In fact, if you ever give a shot, it's attracted to the plastic, so it makes this little curve called a meniscus. And that's caused by water's attractiveness to other things, and that term is called adhesion. Okay, so anyway, and the bonds that are caused by hydrogen having that partial electron charge, that sigma plus charge, these are hydrogen bonds. So these are the four main bonds that are important in living systems. We have covalent polar, we have covalent nonpolar, and we have ionic, and we have hydrogen bonds. Those are the four big ones. And those are the ones you're going to need to know, and what the difference is between the all four of those for the test. All right. So here's some more definitions that you're just going to need to learn. When we transfer electrons between atoms, so in other words, we're making what kind of bonds?
Ionic.
Right. We produce things called cations. Cata means down, like catatonic. And so when you have a cation, anything that has a different charge is called an ion. So you have a cation, it means it's down, which means it's smaller. So which one of these got smaller, sodium or chlorine?
Sodium.
So that's a cation, right? And then ana, like anabolic steroids, what do? They make you bigger, right? So ana means up, like Hans and Franz pump you up. So what happens to chlorine? Did it get bigger or smaller?
Bigger.
Right. So that's an anion. Does that make sense? So things that are positively charged are called cations. Things that are negatively charged are called anions. And unfortunately, you're just going to have to memorize that because that's how scientists talk. Just like doctors run around saying stat. If you don't know what stat is and you're a nurse, you're in trouble. Okay, so we talked about these bonds. Important weak bonds. And weak bonds are important because we want to reverse them, right? You don't want that to be permanent. So the weak bonds are hydrogen bonds and ionic bonds. Don't worry about this. We don't have time to talk about that, but you'll learn that in chemistry. So these transient bonds are important because they can be easily broken. What's the strong bond? The one that's not listed here?
Covalent.
Covalent, yeah. These are really hard to reverse, just like we talked about with cyanide poisoning. So it's really important for cell signaling, right? If you have a red light, you want to be able to turn that to green. So if you have something that is a stop signal, you want to change that to go. Like, for example, if you're drinking milk, you don't need the enzymes to break down milk to be active if you're not drinking milk. So you want them to be off. But if you're drinking milk, you need the enzymes that break down milk to be active. So you need to be able to turn those on. And the only way to do that is to change the ionic bonds or the hydrogen bonds of the particular molecule that turns that switch on or off. So cell signaling is important. The DNA, right? So remember we talked about DNA is a double helix. So think of it as a book, right? What happens if I close the book? So the helix is closed. Can I read the words?
No.
No. If I glued the book shut, like with covalent bonds, would you ever know what the book said? Nope.
No.
So we need to be able to open the book. And the only way to do that is to use weak bonds so that we can open it. And your DNA is actually held together by hydrogen bonds. And you'll see that when we get to chapter 5. And then the three-dimensional shape, we can change that. Or what's the most important thing in biology?
Shape.
Yeah. Shape is everything. So if we can change the shape of a molecule, we can turn it off. And if we change it back, we can turn it back on. And that's how your muscles work. That's how we send electrical signals to our brain and to our nerve and all this other stuff by the changing of the shape of molecules. And as we go through this course, you'll understand that more. All right. So everybody get what hydrogen bonds are? We abbreviate them as H bonds, right? And those are attractions between, usually it's a hydrogen atom that's covalently bonded to another strong electronegative atom. So we talked about water, right? The electrons spend more time around oxygen because it's stronger than hydrogen. And so this gets a partial plus charge. And this gets partial negative charges on the paired electrons. But nitrogen does the same thing. So nitrogen's really electronegative. So electrons spend a lot more time around nitrogen than they do hydrogen. And so what happens to hydrogen? It gets a partial positive charge. And nitrogen gets a partial, can you guess? Negative. Yeah. So hydrogen bonds can be formed. They're usually formed when you have a nitrogen hydrogen compound or oxygen hydrogen compound. And you'll see that when we look at DNA and stuff like that. Remember, hydrogen bonds are weak. They're not anywhere near ionic because remember, to be ionic, you have to transfer a whole electron. So this wouldn't be a partial plus charge. It would be a full-on plus charge. The hydrogen bonds are weaker than ionic bonds, and they're definitely weaker than covalent bonds, about 5% the strength of covalent bonds. So these are really weak biologically. This allows water to maintain its ability to be liquid over a wide range of temperatures. In fact, water is the only substance found on Earth that is found in all three phases: a solid, a liquid, and a gas, all at the same time. And the reason it is because of hydrogen bonds. Now, you might not understand that, but when we get to chapter 3, you will. And it also creates surface tension. So remember we talked about a glass of water is going to look like this. And these hydrogens are going to be pluses. And then we have another one over here, and that's going to be negative. And we have these hydrogen bonds, right? So if you guys want, you can try this experiment at home. Get a paper clip and gently set it in a coffee cup full of water. It can't be one with cuts in it. And, you know, some of them have the little serrations in them. It has to be just a perfectly smooth paper clip, and you can actually get that thing to float. I'm sure you guys have seen water bugs like walk on the surface of water. and stuff like that. And the reason they're able to do that is because water grabs onto other water. You can think about it as like someone doing a stage dive. So if people are all holding hands, what happens to that person that jumps off the stage? They don't fall to the ground, right? But if everybody's holding hands, or if they stop holding hands, then what happens to that person that jumps off the stage?
It'd fall.
Right. So when you look at water, a cup of water, you can think of all of those water molecules are holding hands because of the hydrogen bonds. And so it has a really high surface tension. You would never be able to float a paperclip on something like alcohol that doesn't have hydrogen bonds in it to hold the paperclip up. Those water bugs would never be able to do that. And we'll talk about why water maintains its temperature when we get to chapter 3, but it also has to do with hydrogen bonds. And this is how, patio misters work, how they cool stuff off, why we use water in the radiator of our cars. All of this has to do with hydrogen bonds. All right. We talked about the electronegativities, right? So just remember that if the difference is 0.5 or smaller, then it's polar covalent. Greater than 0.5, it's polar covalent, 0.5 or greater. If it's less than 0.5, then it's, what do we call it? Non-polar, right? And then if it's big, and so we kind of said that there's leeway here, so it can be somewhere between 2.1, 2.5, or 3, then it's ionic. All right. So there's a reason that you guys breathe oxygen in order to survive. And that has to do with the movement of electrons. So you guys will have a table for this, but I know it. Oxygen's electronegativity is 3.5. Carbon's electronegativity is 2.5. So which one of these is more able to grab and keep electrons? Oxygen or carbon?
Carbon.
Which one's stronger? It's more able to grab electrons.
Oxygen?
Yeah, because this number is bigger. So oxygen's always going to be able to pull electrons towards it from carbon. And so this is the natural way things work. Just like if I poured water on top of a mountain, would it run uphill or downhill?
Downhill.
Yeah. And so electrons are naturally going to go from a weaker element to a stronger element. So when you guys breathe oxygen, what you're really doing, and you're going to learn this in chapter 9, is you're taking electrons off carbon, which is in the food you eat, like glucose. You're taking electrons off carbon and you're putting it on the oxygen that you breathe, and that causes electrons to flow. And what do we call flowing electrons? Do you guys know? I'll give you a hint. You use it to power your refrigerator, to charge your cell phone, to make your vacuum cleaner run.
Electricity.
Yeah, moving electrons are electricity. And so what you're generating is electricity inside your cells right now. That's how you're able to live and see and think. it's moving electrons from carbon to oxygen. And so that is with the gradient, carbon to oxygen, and that releases energy. You guys know electricity has energy. So if we make electricity, we're going to have energy. Water naturally runs downhill, so we're going to get this energy for free, like the dam, like Hoover Dam. As long as we eat food and breathe air, we can make energy. And then photosynthesis is taking electrons off of oxygen and putting it on carbon. Is that a natural thing?
No.
No, it would be like you pouring water and it running uphill. Can you get water to go uphill?
Not really.
You can, but you have to carry it, right? So you have to put energy in, or you'd have to pump it. So that's against the gradient to go from oxygen to carbon, and that requires energy. Plants are taking carbon out of the air and combining that so they're taking CO2 and they're combining that, and you're going to learn that in chapter 10. And they're splitting oxygen to release. So they need to put electrons onto carbon from oxygen. And again, we'll go over this in chapter 10. But the reason I'm telling you this is that I want you to see that this goes against the gradient. And so where would the energy come from to go against the gradient for photosynthesis? The answer is the sun, right? So sunlight allows this to occur. Okay, so let's pick this up on what is today? Thursday. So we'll pick this up on Tuesday. You guys have a good weekend. I'm going to jump over to office hours in case anyone has any questions. But we'll pick up on chemical reactions on Tuesday. Do you guys have any questions?
No.
All right. Have a good weekend. I'll see you then.
Thank you. You too.
Thank you.